Hello. Oh, sorry.
Good morning, Rahul.
Oh, I'm sorry. I wasn't seeing that thing, so I didn't admit you in. Okay. Okay.
Oh, that's all good. Uh, no worries. Um, I'll get the people from outside and we can get
Okay.
started.
Okay.
All right. Good morning, everyone. Welcome to day 3, week 2, MLSS Melbourne Conferences. We had a great talk by Rao yesterday already on planning and with LLMs, and I think today's topic will dive even deeper in the reasoning capabilities. And yeah, I'm really excited. Please give it up and welcome Rao.
Thank you. Thank you, folks. You can hear me, right?
Yes.
Okay, great. Thank you. So once again, the slides are here. I also posted them to the Slack in case you want to follow along. And also, yeah. So before I started, I thought I'll ask if anybody has any questions from yesterday that they didn't have time to ask. So if anybody has any questions, maybe they can ask before we get started with today's discussion. And also, I should mention, I hope you are noticing that I'm wearing Australia t-shirts. Yesterday I wore one, and today I'm wearing my Uluru t-shirt. I hope you are appreciating the fact that even though I'm not in Melbourne, I'm sort of in spirit in Melbourne with the Australian t-shirts. But anyway, if there are any questions, maybe. If not, I will continue.
Any questions? I feel like we're good to go.
Okay, great. Yeah, again, as usual, if there are questions, ask me, and also you can, post on the Slack, and of course, towards the end, again, we'll have time. So I wanted to bring up a few things that sort of came up as we were discussing yesterday. That kind of is, the first couple of minutes I want to kind of add to yesterday's lecture before taking off into a slightly different direction in terms of reasoning traces and so on. So one thing that I kind of wanted to put in the introductory slides that I forgot to mention yesterday essentially is the sort of the standard LLMs, at least their approximate retrieval kind of nature appends our intuitions regarding their guesses. So one of the things I did mention without the slide, I just put it there, that computational complexity of the underlying task has really no bearing on the LLM guesses. So whether it is semi-decidable or undecidable or like O1, LLM takes the same amount of time to make hazards its guess. And sometimes the guess is correct, sometimes the guess is wrong. And whether or not the guess is correct doesn't depend on how hard the problem is. It depends more on how representative that problem is in the training data that it has. So the corollary of that is that the usual problem characteristics, such as stochasticity, partial observability, etc., that typically make decision problems more intractable, they are, and computationally harder, they don't necessarily make LLMs any harder. So for example, say, okay, after that we find that LLMs are not doing well on deterministic planning, if somebody kind of comes up with some kind of a stochastic planning scenario where again there are no sub-goal interactions and tries to see that, look, it has a higher accuracy on this harder problem. Well, the problem is harder computationally. It's not really affected, it doesn't affect how the LLM would provide its guesses. It is much more dependent on its training data. That's worthwhile, keeping in mind. This is again for standard LLMs, and to some extent, it's also true for reasoning models and post-trained models, because it depends on what you have post-trained them on. The other thing to keep in mind equally is the background knowledge is much easier for LLMs, sort of approximately speaking. So as I was saying earlier, yesterday, as in response to one of the questions, you could basically ask them lots and lots of things about what's the plan, what is the domain model for the plan, what is the abstract strategy. And similarly, you can ask them about common sense questions. You can ask them about domain knowledge, theory of mind, analogies, and they do reasonably okay. There's no guarantees. And in general, basically, and of course, they have amazing summarization, elaboration, format change, etc. So this is something to keep in mind, that they are essentially sort of jack of all trades, but unfortunately not guaranteed master of any. Whereas comparatively speaking, the classical, whatever the traditional systems tend to be master of one trade and not particularly good at anything else. That's worthwhile keeping in mind. The other thing that I wanted to mention yesterday is this is a couple of slides that I probably should have mentioned before getting into planning, but I think it's worthwhile still saying it here, that in general, planning and decision making, sequential decision making is basically given a set of objectives, come up with a course of actions, which are a policy, a plan, and a policy. There is a difference. There's no really difference. A plan is just a sequence of actions. A policy says, if you know the state, what is the action you are supposed to do in that state. Okay, so a plan is really a partial policy because it's saying if you are in one of these states, then you should be doing these actions, or you can just do these actions with your eyes closed, and it will still reach the final goal state. And one of the interesting things typically is that planning decision-making problems traditionally have assumed that you know the actions and you know some sort of a reward metric, and then you're trying to find the optimal policy. Sort of a MacGyver planning, for those of you who know the MacGyver, the TV series, is this stuff where you don't even know what are all the actions, and essentially the system is trying to figure out arbitrary actions that you didn't even think about. That's most of the point of MacGyver, the series, for those of you who have seen. And in general, actually, LLMs are actually good at that because, as I said, if they don't know, they may have an actually approximate domain model for even open-ended domains, but there's no guarantees. I mentioned also that scheduling is different from planning, and in general, given a set of tasks and jobs and a choice of actions for accomplishing each of the tasks, we basically just have to assign actions to the task so that there are no undesired interactions. That's what scheduling is. And sort of planning is more general because there's a cascaded choice that goes on. And the reinforcement learning, model-based reinforcement learning, essentially can be thought of as learning the model basically as you go along. So that sort of model-based reinforcement learning and planning have very strong connections. This picture just shows that scheduling is one end in terms of the action choices and how many new actions that you have to introduce into the plan, and planning is in the other end. So it's like they are sort of in a spectrum, but scheduling tends to be constraint satisfaction problems. Planning typically tend to have this precondition cascading. You put in an action to support some goal, and then you have to once consider the preconditions of that action onwards. One interesting thing actually is even in the simplest case of what's been called the STRIPS action language, which is sort of what we were talking about in blocks world and logistics domain yesterday. The Tower of Hanoi can be written as one of the problems there. And one interesting ramification of that actually is, as you know, Tower of Hanoi problem, the plan is exponentially long in the size of the input specification. So that is actually one way of realizing that just coming up with the plan is not even in the computational class NP, because if I give you a plan, checking if it's correct or not might take exponential time because the plan is exponentially long. So that's worthwhile keeping in mind. And a couple of other things I mentioned in without slides yesterday, but I just wanted to bring up here is, an environment is ergodic if the agent can reach any state of the environment from any other state with positive probability. As a corollary, in non-ergodic environments, agents can get stuck in some states or some groups of states. Planning is in some sense most crucial in non-ergodic environments because you want to know what you're going to do before you start executing. In a completely ergodic environments, you can blunder your way through. You can make various actions and you will never die in essence because you will not get into a state from which you can't come out. So you will have inoptimal plans, but there is no problem about actually getting stuck in a state. to give a sense of what the sort of an ergodic, non-ergodic world looks like. Of course, real world is non-ergodic, but I also mentioned yesterday that there is this very simple toy problem called Sokoban, and I wanted to show you like an animation of Sokoban. Sokoban is a thing where you have some boxes and you need to push those boxes into the right configuration. The problem basically is the agent can only push the boxes. The agent cannot pull them. And so if you kind of push them into the wrong place, if you started executing the plan without actually making one, then if you push them into the wrong place, you cannot bring it out of that place. So that's how actually Sokoban becomes a non-ergodic domain. And you will see that LLMs do much, much worse in Sokoban style domains compared to like blocks world and even mystery blocks world. The other thing that's kind of relevant here is the robustness of a plan is informally the probability that it achieves its objectives without failing or getting stuck. In deterministic environments, correctness is just a binary measure of robustness. If the plan is correct, then it will work. If not, it won't work. In a stochastic environment, the same plan might work sometimes, not work some other times because of how the action transitions are themselves stochastic. Okay, so in non-ergodic environments, when you have a plan, you want to have a high degree of robustness so that that plan may not, in fact, you might have a plan which sometimes actually can get into states that will sort of be, from which you can't come out. So for example, if you are running on a very steep trail in Grand Canyon, basically, there is a possibility because it's a stochastic transition, there's a possibility that you might actually lose your balance and then fall down the canyon. And once you fall down the canyon, it's essentially you're in a state from which you can't come back onto the trail. As a side effect, you're also dead. So the point being that you want to have higher robustness, and that's probably the reason why people will walk slowly on the trails, if they're not sure about their footing on the trail. While robustness is a measure of correctness of the plan, there is this orthogonal thing called quality of the plan. Quality is really more about its style as it is desired by the agent or the problem specifier than about whether it's correct. So you can have a correct plan which is actually achieving the goal, but it's not, it has some undesirable characteristics as far as the humans are concerned. I showed you an example yesterday where a robot is giving you, for example, a pair of scissors with the pointy end towards you. Quality typically captures these intangibles such as implicit, unstated preferences. For example, in a travel plan to go from Phoenix to Vienna or Melbourne, going partway by walk, partway by bike, partway by car, etc., can finally get me to the place, but it may be considered a pretty undesirable plan. It works, but it's not a stylistically good plan. Similarly, if you write like a Python program with way too many go-to sorts of statements, or a Pascal program with many go-to statements, that may well be correct, but it's not a good style. And in general, one of the interesting things is LLMs trained there as they are on the web scale corpora of our collective output, they tend to capture the style preferences quite well. And in particular, there's nothing else that's actually a good competition. So this has been said also in the program synthesis literature. For example, people have said that even when the program doesn't work, when LLMs generate programs, even when they don't work, if you look at the programs, they look like the kind of programs people might have written. Not surprisingly, because they've been trained on the entire GitHub corpus, for example, which are human written programs. So it's worthwhile remembering this is actually this quality versus correctness is a variation of form and factuality and style and content. That there was a slide that I had in the yesterday. So that is kind of a trade-off that you want to keep in mind. Of course, that's a Sokoban. And then the last thing in this part is I want you to think about world models, verifiers, and simulators. We talked about verifiers and simulators yesterday already. Verifiers, of course, is given a plan, it will tell you whether it's correct or wrong. A simulator essentially kind of simulates the plan and tells you whether it reached a certain goal state or not. And both verifiers and simulators typically come from outside, and they're not coming directly out of LLMs. One of the interesting question is, for traditional planners, the way they actually generate the plan is they have an internal world model with respect to which they can check if the plan is likely to succeed. Okay, so one of the big issues, so that model can be something that's supplied, such as for traditional planners, there might be like you can have a PDDL model or SMT models, which is the SAT modulo theory models. You can also give them domain simulators, or they may be learned directly by the agent by trial and error over the real world. This is what RL does. The actual agent does experiments in the real world and learns the transition of the world. The interesting question, of course, is LLMs are not acting in the world. LLMs are trying to look at you acting in the world. Whatever you have written is your experiences in the world, and they're trying to kind of induce something out of that. Everybody knows that at least standard LLMs are not actually doing actions in the world and learning from that. Because at the inference stage, basically, there is really no change in the weights that's going on. So the one big unresolved question with LLMs is to what extent they have a robust internal model of the world. The fact that the plans tend to be, the plans that they're making are kind of pretty brittle. That's what I was telling you yesterday. Tells you that maybe they don't have particularly good models of the world. And there have been other people who have done work showing that the models that LLMs learn, for example, in Manhattan, you can give tons and tons of travel sequences from if you go from here to here, and what are the streets you're taking, and then you train the LLM from that, and then it will actually give you a pretty good travel plan for any arbitrary source and destination pairs. But if you actually look at what does its internal model look like, essentially it looks like completely messed up compared to the real Manhattan. For example, I assume you guys know that Manhattan mostly is, it's a grid of avenues and streets, except a couple of roads like Broadway, which actually cut through in a diagonal way. In fact, because of which we have the Manhattan distance, which basically doesn't count diagonal moves. In fact, there's work basically that WAFA, etc., show that LLMs don't actually learn the Manhattan model and model of the map, and yet get reasonable accuracy in terms of the start to goal paths. So one big question, of course, is whether LLMs are really, we do realize that standard LLMs are bad in getting the plans correctly. The question is, to what extent is it actually connected to the fact that they don't have good world models? Now, shifting from that, one thing that's actually interesting is that you can actually, something like traditional planners, which like say have a PDDL model, right? And then that PDDL model, typically people have to write. They'll sit down and write the model saying, these are the actions, these are preconditions, these are the effects. And as I mentioned, you can use LLMs to actually generate a guess of the domain model. And one of the things you can do is you can actually use recursively the same LLM modulo framework, where the LLM actually now guesses the domain model, not the plan, in terms of the actions, preconditions, and effects. And then you correct them, either the human or many of the local correctness checks can be made by various critics. And you could do this. And in fact, we have a paper in NeurIPS 2023 that shows how you can use LLMs themselves to make the process of getting the PDDL model faster. Instead of actually, humans having to write it, you can, accelerate it, because they will give you some approximate set of actions, their preconditions and effects. And then the human in the loop basically just has to make sure, human in the loop or some additional verifiers or critics has to make sure that there's no egregious errors in them. Okay, so that is actually something that was, it's a paper in NeurIPS 23, and there are other people who have done this sort of a thing. That is, you're using LLMs not just to generate plans, but also generate domain models. And in fact, the domain models actually could be useful in particular to check if, in fact, a plan is correct. The way you normally check whether a plan is correct is you take the plan, you take the domain model, simulate the plan with respect to the domain model, and see if it reaches the goal state. And so, in fact, the domain model essentially will be, and then to do that, there is this, in the kind of a planning scenarios, there is this thing called val, something called a validator or called val. And the val is like the Python interpreter, and the the plan that the large language model guessed is like the program, and you are checking whether or not the unit test is the initial state and the goal state. If it reaches actually after the simulation, it reaches the goal state, then you will say that the plan is correct. That's basically what is happening in the context of verifiers there. So essentially, you can basically extract the domain models out of LLMs. That's also possible. Okay, so there is more information on this paper about how good those domain models are and how good the quality of those models is, etc. And that sort of a thing is possible. One last thing I wanted to mention before I go into the more reasoning traces stuff today is this is something that actually I think there was a question at the end, I think by Doug Aberdeen was asking. So how does like planning and RL kind of change to some extent given that you have LLMs? And the big issue to keep in mind is that before LLMs, for too long, both planning and RL kept falling to the bottom level in terms of not taking any knowledge from outside. Because in general, if you input any knowledge, it was considered like cheating. So the idea was try to give as little domain knowledge as possible to these models and try to make them learn everything from scratch. So for example, deep reinforcement learning tries to learn things from just pixel level knowledge, for example. And that tends to be actually very, very, very inefficient. And so what changed is with the LLMs, in the past, if you needed like a domain knowledge, you had to ask a human, and that was considered cheating. But everybody is okay with you asking LLMs for the same knowledge. And LLMs actually have been trained on all humans' digital traces. And so it's this ironic thing that you are not allowed to ask a single human about how the domain model for this is or how the transition model for this problem is, but you're okay to ask an entire LLM, an LLM which has been trained on the entire humanity's digital traces. So one of the interesting things about how to use them to improve planning and RL algorithms in the era of LLMs is that million-dollar question is, how would you do planning if you have a doddering, know-it-all uncle ready to give you any kind of knowledge, actions and effects, task reduction schemas, cases, etc., but with no guarantees? And I would argue that actually something like LLM modulo with like domains extracted also from LLMs would actually provide a way of doing that. And so it's sort of one more high-level view of thinking about what's the role LLMs play in planning models. So now I'm going to shift gears and look at the bigger theme to some extent based on yesterday and also part of today's thing is in the context of planning and reasoning problems, in particular planning, because I'm talking about planning mostly, one question is we kind of know that they'll guess plans. The thing that we don't know is whether the plans that they guess are going to be correct. And can we give guarantees, prior guarantees that they will be likely to be correct? And so basically the overview essentially is we started with standard LLMs that they're known to have questionable accuracy on reasoning problems. Then test time scaling with verifiers in the loop were proposed. That's what we talked about yesterday. And that improves uses generate test kind of a paradigm to increase the guarantee that the plan that you're sending out is correct. But test time scaling consumes too much user facing time. And then, so the reasoning model started, but the reasoning models can be thought in terms of this post-training of the test time scaling into the reasoning, into the generator. But then they have a better generator, but they still don't have guarantees that the plans are correct. And so if you put verifiers back into the loop with the reasoning models, that will help again. That is LRM modulo. But then often we may not have sound and complete verifiers. And the question is, can we verify maybe either partially or can we verify some of the process with which the solution has been arrived at? And a tempting technique there becomes assessing the correctness of the solution by evaluating the thought process of the LLM, because that reasoning models output these think traces, and maybe the think traces can be evaluated to see whether I should trust the solution because it's thinking right. Okay. And much of what I'll be doing today is to point out that that's a very, very worrisome direction, because actually think traces don't necessarily have to have any semantics at all. And then towards the end, I'll talk about some new ideas we are playing with, such as meta prompting, which actually kind of provides process level guidance from outside. Okay. So then basically the first parts, I mean, again, basically, if you look at the standard LLMs, they're known to have questionable accuracy and reasoning problems. I showed you that yesterday. And that I showed you that the test time scaling techniques are actually a way of increasing the correctness by doing this sort of a generate test framework. And I focused on LLM modulo as a way, in fact, because they have a verifier or a bank of verifiers. And then you talk about generate test framework. But then we also talked about the fact that test time scaling, the user has to wait for this loop to end, and the verifier saying that the plan that you came up with is actually correct. That's kind of costly. And so a new breed of reasoning models compile the test time scaling into generator via post-training. And of course, that's the post-training methods that we talked about, and we talked about the DeepSeek R1, RL, etc. And I did point out that LRMs actually are much better in terms of, compared to LLMs, in terms of their generative accuracy for at least smaller problems, but their accuracy also falls down as the size of the problem increases, which kind of brings up, which kind of can be understood in terms of what I explained yesterday, that they're not learning the algorithm and kind of running the algorithm. They're learning to like separately compile how to generate larger and larger plans. So if they can generate plans of length 2 or 4, that doesn't necessarily mean that they know how to generate the lengths of the plans of length 7 and 8, etc. Because it's the incremental compilation that's sort of going on. And then we talked about the fact that you can actually put the LRMs themselves in the LLM modulo framework with the LRM there, and that can actually basically includes both post-training in coming up with the LRM and test time scaling in terms of doing inference time verification. And that does give higher accuracy even compared to these LRMs like O1 and O1 mini and O1 preview. That's basically a quick review of what we did yesterday. Now, as I was saying, maybe what if we don't have good enough verifiers? Of course, you can have partial verifiers, which is better than not having any verifiers. But another tempting thing that came up is what if we can verify the process instead, the process with which LLMs come up with a solution. And in talking about the process, we tend to think about these think traces that you all know that DeepSeek R1, for example, generates on the way to the solution, and being called chains of thought, etc. So the question is whether these chains of thought can be looked at and somehow either automatically or by humans validated. And you, in some sense, because you can't validate the solution itself, you try to validate the process and get indirect trust in the solution. The problem, and in fact, I'll spend close to 40 minutes on this, or maybe more, is to show that intermediate traces don't actually have much of a semantics, and they don't have to have any semantics. They need to help the LLM. They don't necessarily have to help humans or any verifiers in the loop. So that is actually a big, we're basically going to talk about that part now. And then, this is sort of based on a bunch of papers that we wrote in the last year, several of which were presented at NeurIPS workshops in December. So I'm going to walk you through this. And before that, I want you to kind of understand that there are two notions of intermediate token interpretability, interpreting how intermediate tokens seem to be helping the performance of LLMs. That sort of mechanistic interpretability studies, that is worthwhile understanding. Why is it that mumbling to itself is helping the LLM generate a completion after the mumbling that's likely to be a solution with higher probability than without mumbling? This much is well known too, that basically if you train models with or without intermediate tokens, the ones trained with intermediate tokens seem to do well. That much is universally understood, and it is worthwhile understanding why is that happening. The other part is because the models basically give these intermediate traces that kind of look like in English. In particular, actually, DeepSeek R1 went out of its way to kind of make its first model R0 generate only English to get R1, and that to do that they kind of SFT'd R0 with large number of human generated English traces so that it actually provides English looking intermediate traces. And then they start talking about things like the aha movement and the model saying, let me backtrack, let me verify, let me reflect, etc. This all looks like people actually solving the problem, and this has become a huge issue, sort of the expectation that somehow looking at the intermediate tokens will be giving you additional information about how LLM is actually solving the problem. And maybe if the intermediate tokens are right, maybe the solution is kind of going to be right. The problem that I will upfront, the problem is there's no reason to believe that this is going to be true, because if you remember, in case you know DeepSeek R1, it is actually trained on outcome reward. It only looks at whether for every trajectory, if it ends in the solution, it doesn't at all look at the intermediate tokens. So whatever is being said in the intermediate tokens is not actually taking part in the learning process at all. So there is actually it's kind of questionable to assume that somehow magically these tokens that are, in the intermediate tokens wound up having, meaning. So we were skeptical, but lots of people actually think they do have semantics. So for example, DeepSeek itself talked about aha moments, thoughts, the reasoning behaviors. Some people have done like syntactic analysis of the thinking traces to see, what phases are there, how many times is it saying I'm backtracking, etc., etc. So there's a whole bunch of this sort of work that was going on. So the question, of course, is, do we really believe that post-trained models are really generating reasoning traces that will actually kind of, in some logical way or causally, lead to the solution? And so for that, part of it is you actually check if, in fact, the reasoning trace is correct and it leads to the solution that it is actually producing. Now, the problem, of course, is nobody really does that. It's not done in the learning, and it certainly is not done in the inference stage in any systematic way. And you might say, well, look, people do look at the intermediate traces for things like R1. Why can't that be a way to do it? So here is an R1, DeepSeek R1, because remember, one other thing is to understand that only DeepSeek R1 actually gives you the intermediate traces. All the frontier models like, like Gemini and O1, O3, and also, of course, Anthropic's Claude, they don't show the intermediate traces at all because they say that's like proprietary. So DeepSeek R1 actually shows the intermediate traces. And, most of the research community has been looking at these and thinking, look, that thing is in English. So here is actually a simple problem that has something about a mystery domain, blocks world mystery domain blocks world problem. And, before giving the solution, the model puts out this kind of English stuff. And you look at it, it looks, wow, this is like English. It say my goal is to have object C, crave object A. The possible actions are attack, feast, succumb, overcome. It looks almost as if it is thinking like the way you would be thinking. And the problem, of course, is, have you checked if these thoughts directly lead to the solution? For that, you actually have to walk through each of the things that it is saying. And the problem is, even for this simple problem, this is just the first page of the trace. That's the second page. That's the third page. That's the fourth page. That's the fifth page. So 5 full pages of mind-numbing pseudo-English, right? And nobody actually checked to see if that whole thing led to the solution it produced, it proposed. And so the question is, obviously, this kind of a mumbling is helping R1 in terms of producing the final correct solution. Nobody's questioning that, because accuracy, post facto accuracy, has shown that it seems to have higher accuracy. But saying that somehow the intermediate traces caused this and they can actually have interpretable meaning from the human side, or even verifier side, is a very questionable statement. Now, in fact, as I said, for basically Claude and OpenAI's models, etc., they no longer show the intermediate traces at all. Actually, they only show what's called a summary, and nobody really knows how they generated the summary. And in fact, sometimes even the summaries go off the deep end. So for example, this is Daniel Late, who is a mathematician who uses these for math proofs. And he basically was looking at its quote unquote summary of its thinking process. And it's first talking about kind of something related to the problem, such as differential ties to row equivalent weakly conforming harmonic map, and then suddenly changes its mind and say, let me see, producing an operator for a kid show involves selecting a fantastic fees, securing rights, etc., etc. So it suddenly starts talking about something different, even at the summary, not even at the actual intermediate traces. Interestingly, people actually try to make lemonade out of this kind of an issue too. There is actually a recent paper from Google which basically says that the fact that there are very diversified stuff going on in the intermediate tokens, it's almost schizophrenic, diversified things going on in the intermediate tokens might mean that is the reason they get actually the intelligence. And there is this paper that you can look up which says reasoning models generate societies of thought. And what they actually do is they look at, because they're from Google, they can actually look at the full reasoning traces of their models, and they try to see how many times the topic is changing or the perspective is changing, and they count that and they kind of find a correlation between that and the accuracy, and they make this argument that actually it's the being schizophrenic that seems to be helping the model to be more intelligent, quote unquote, with higher accuracy. This is what the claim is. Now, suppose I wanted to question this. It's a reasonable thing in science. You want to question things, right? So how would you actually go about questioning this? So obviously, the traces that are like 6 pages long, that basically we showed about the DeepSeek R1. I don't know how to actually verify that, because it's just basically pseudo English and there's no verifier for that at all. So one idea that we came up with essentially is, imagine you trained an empty transformer, because after all, LLMs are transformers trained on the, basically the entire web of knowledge. So if you trained an empty transformer with a particular class of problems, in particular, what we'll talk about is an A-star search trying to solve maze problems. So we generate mazes of different kinds. They are mazes from very different distributions, acyclic mazes, cave generation based mazes, and even no maze mazes, basically just free space. And you generate these mazes, you have the A-star search solve the problem from start to, you pick a start and goal in each of the mazes, and then you make them solve the problem, that is basically find the optimal path. And then A-star search, any algorithm essentially has a trace. So A-star search will have open and closed list manipulations. So I can take that as the trace of the A-star search solving this problem. And so I have the prompt, which is this entire maze problem and the start and goal state. And the intermediate traces are the A-star search, closed list, open list manipulations, and the final solution is, of course, the final path. We take about 500,000 of these traces, and with all correct A-star search, intermediate traces, and then we train a Quen 500 million parameter model. And so the question, of course, there's more information about the actual details. It's a half a billion parameter model. And the vocabulary is actually custom vocabulary in this case, because you only have to talk in terms of, because this particular class of problems. I will talk to you about how these things work on pre-trained models. But right now, bear with me and think of this sort of model organism study where you are looking at a model that started with an empty transformer. You trained it with the data that you know, and then you are testing it. Okay. Again, training data, there was a 500K maze instances generated using a specific maze generation algorithm. And then you have A-star search solve it, take the traces as well as the correct solution. And now you have one training instance. You have 500K training instances. You're going to SFT the heck out. And later on, we'll also do RL the heck out of the model with respect to this training data. Okay, so the question then is, what I want to ask is, now that I have a model which has been trained like this, now if I give it, mazes with start and goal, not surprisingly, it will actually hazard guesses about what the correct path is, and it will actually do intermediate traces tokens before giving the final solution, just like DeepSeek R1 does. And I can actually check if, in fact, because these traces actually mean something to the A-star search, so I can check if whether the traces are actually valid. That means if A-star search looks at this trace that the transformer generated, And if it actually simulates it, will it have reached the same solution that the transformer guessed? Okay. And in terms of the number of problems where the transformer is correct, what is the, so this picture is basically showing the total times, under, basically one of the things we get to do is we can actually compare performance between in distribution as versus out of distribution. You can generate a model with Wilson mazes and test it on Kruskal, depth DFS models, etc. So you're also getting this, out of distribution performance. And there are two numbers in each bar. One, the top number essentially is the percentage of the problems that were for which it gave the accurate, path for the test cases. There are about 1,000 test cases that, for each of these models, for each of these distributions. So, for example, 79.9% of the cases, Wilson model, for example, gives correct solutions, and 97.7% of the time when it gives the correct solution, it also gave a trace that actually would have led to that solution according to A star. That looks promising. But the problem is, as you go towards larger and larger problems, the correlation between trace validity and solution correctness deteriorates pretty badly. For example, if you look at that harder 2 instances, which is the rightmost in this slide, there are about 16.2% of the problems it was actually able to solve correctly. By the way, the numbers are, the lower number is accuracy, the upper number is the validity, among the correct solutions, what percentage have valid traces. So you have 16.2% correct solutions, but only half of them have valid traces. So basically, the trace validity and the solution accuracy is getting, it's not connected. It's not perfect. It's actually diverging as the problem complexity increases. So then we ask this other relevant question. We took care to train the model with correct traces from A star search. What if you actually trained the model with incorrect traces to begin with? Would it have done just as well, or at least would have done somewhere near that? So for that, what we did was we took many ways of introducing noise in the traces. The one we did is like a pretty drastic noise version, which is called swap traces. So if you have a problem 1, the trace for the problem 1 and the A star search solution for the problem 1, and similarly problem 2, trace for problem 2, A star search solution for problem 2, I swap the intermediate tokens for these two problems. That means problem 1 will have the trace of problem 2, solution of problem 1. And problem 2 will have the trace of problem 1 and solution of problem 2. And that means everybody is getting the wrong trace in the training data. And we now retrain the models, with these swapped traces. So empty transformers are trained with these swapped traces. And the strange thing is, not only does the performance not worsen, it actually becomes much better. It's actually even better. That means the swapped models do better in terms of accuracy. And of course, the correlation to the correctness or the validity of the trace is much worse in this case, because we are checking after it provides the solution in the inference stage, is the trace that it produced actually leading to that solution. And since it's been actually trained with the swap traces, it gives stuff. Even when it's trained with the correct traces, it was giving invalid traces in the inference stage. And not surprisingly, it gives even more invalid traces in this particular scenario, where the swap model has been trained with the completely swapped traces for each problem. So that sort of makes you wonder what exactly matters. In fact, even if you actually trained the model with incorrect traces, probably incorrect traces, it seems to be doing well. So we did this another experiment where we considered starting from 100% correct traces to 100% swap traces. So the x-axis is the percentage of swap traces in the training data. So 0 basically means it's fully correct traces. 100 means it's fully swap traces. In between, it's 25% means 75% have correct traces and 25% have swap traces. And for each of these cases, we trained a different transformer. And so basically, then we check their accuracy on the test problems and also the validity. And one of the things, of course, is the validity. You notice on the right-hand side, validity sort of monotonically falls because the models are being trained with more and more noisy traces. So the traces that are generating in the inference stage don't actually correspond to any valid traces by A-star search standards. The mind-blowing thing to some extent is the U-curve on the left-hand side, which kind of shows that the accuracy is high when it's fully correct, high again when it is fully incorrect, and it's lower, it's like a U-shape when it's a mix of correct and incorrect traces. That sort of gives you a potential hypothesis that what is actually probably happening is that the model really just needs some scaffold, some consistent scaffold to overfit itself to the signal of the verifier as far as the trace, the solution part is concerned. And that's really is more important than whether the traces that it is outputting actually, whether it was either trained on or outputting actually have any meaning, which is a very different thing from what people are assuming. So this is worthwhile looking at it. So this was, as I said, presented at NeurIPS in 2 workshops. One other thing related to this exact idea is connected to this notion of computational complexity of the problem versus the length of the intermediate traces. There's been this general idea that reasoning models will produce longer traces if the problem is hard and shorter traces if the problem is easy. The question is, problem is hard versus easy computationally, or is it with respect to your memory? Most people assume it is with respect to computational complexity of the problem. But unfortunately, that's just not true. In fact, if you take a model that's trained on the Wilson mazes, which look reasonably painfully, complicated, and you test it on the right-hand side, top right-hand side model, which is called the no maze mazes, where essentially S and G are in free space. If S and G are in free space, all of you know that path planning is a trivial problem. Basically, A-star search will just make a beeline directly to the goal. There's really not much of a search that needs to be done. And so A-star search trace length is actually very small, and yet the model trained on the real, more complex puzzles just fails pretty badly on these trivial puzzles, which should not be surprising because essentially it sort of is. It's more important that it's kind of in distribution. And what you mean by in distribution is it looks like the kind of models that it's more kind of mazes it's been trained on. The lower 2 plots show on the x-axis for a bunch of problems, not just the ones like the free space problems, the amount of time that the trace length that A-star search produced in solving that problem, which is a pretty true indication of how hard it is computationally, and the number of tokens that were produced by the transformer during the inference. And you notice that if it is actually correlated, there should be some x equal to y line. And you notice that the x equal to y line is actually lower down because the scales are different, because the transformer is actually producing way more tokens than A-star search is producing for many of the problems. And you will also notice that there really is no correlation between the problem complexity, which is x-axis, and the tokens, length of tokens produced, which is the y-axis. That makes you wonder once again that in fact intermediate tokens should not be outlaid, sort of overlaid with any claims about semantics of either semantics of the computational complexity or about interpretability to the final user. Okay. So that was also presented in NeurIPS. Now, one other question is, how will this all be affected when you do RL post-training? We were talking up until now about just SFTing with traces that we have, basically trained the model on. right? So if you do the same thing but with RL post training, what would change? So for that, actually, I'll make a small digression and talk a little bit more about the DeepSeek R1's RL, because that's the one that's become very popular. People all use it. So one question, of course, is, as I mentioned yesterday, in the case of DeepSeek R1's RL, you essentially, what it does is it picks a synthetic problem instance and it makes the base model generate k trajectories. Each of these trajectories have think traces followed by the solution part, think part followed by the solution part. And the verifier, the rule-based verifier, they call it, that's why RLVR, basically evaluates the trajectories, the solution part of each of the trajectories, and gives it reward if it actually ends in the correct solution. Otherwise, it has zero reward. There's some minor changes about style being given some reward, format being given some reward, but mostly actual reward signal is correctness of the solution. That's what has been called RLVR. And then you use policy gradient methods to push the LLM parameters towards the good trajectories. There is a bunch of policy gradient methods, PPO, and then GRPO is essentially, and the PPO tends to kind of have a separate critique network that learns how to predict the value of a state, so that you can see the advantage in terms of doing this action in this state, to the extent how much of an advantage you get for doing this action versus the average value that you can get from that state. Instead of learning that critique network, they try to do this group average over the trajectories. Okay, now, so DeepSeek R1, one thing that you want to understand is actually, it's a very strange kind of RL problem to some extent. If you think in terms of essentially sequential decision-making problems, you have to realize that what DeepSeek R1 is doing is a formulation where essentially there's really no difference between states and actions. States are a sequence of tokens. The initial state is a sequence of tokens corresponding to the prompt. The next token that of the prompt completion, let's say, is A0, then the next state will be the original prompt plus A0 concatenated. And then if you do A1, then the next state will be the original prompt plus A0 plus A1 concatenated. So basically, states and actions are connected essentially. And what's also important is it's sort of path independent, that if you are actually in a particular context, then you know how you got to that context. You essentially added tokens exactly in the order they are appearing in that sequence. And so it really, this is actually more closer to the contextual bandits of what the people call RL0 than normal sequential decision-making RL formulations. And yet, if you read the papers, most people tend to analyze it as if it is sequential decision-making RL. And one other big issue that they wind up doing is that, unlike normal RL, where if you have reward after you reach the final state, then RL has to figure out how to provide the credit to the intermediate states and actions. It can't just assume that the reward is equally divided over the trajectory. But it turns out that what actually GRPO does in DeepSeek R1 is it makes everybody gets the same reward. It's almost as if every token that is in the winning trajectory gets a badge of being a winning token. And if you do that, not surprisingly, you should realize that even though DeepSeek R1 says the RL is only outcome reward based and we're only looking at the solution part of it, it's actually looking at the entire sequence, because you're giving the same reward to the entire sequence. And when you are training the model, you're almost doing something extremely close to it, SFT. The only difference is it's a kind of a filtered on-policy version of iterative SFT. So you can, as long as all that is common is the verifier, and if you can start with the verifier and this MDP formulation and reward split equally and group-based advantage, you can get DeepSeek R1's GRPO, but you can get to the other side with the same verifier with an SFT ideas. You basically generate, filter using the verifier to remove any trajectories that are not working. And of course, you can do a variation of that where you can keep the failing trajectories with the zero reward in the in the training part. But mostly imagine you filter it away, and then you assign positive weights to the correct ones, negative weights to the incorrect trajectories, and then you do on policy SFT iteratively. And if you do this, basically they are the same, both theoretically and it turns out that they're also same in terms of performance. So filtered iterative SFT and GRPO are essentially same in terms of performance. And there's a paper that we show this. And one interesting point about this connection is that you can also show that this particular way of training, either from the SFT point of view or RL point of view, indirectly incentivizes the model to produce more and more tokens if it is actually not going towards the solution. That is the solution that's likely to get verifier saying yes. So, in the DeepSeek R1 paper, basically they make a big deal about the fact that over the epochs of training, the intermediate token lengths increase. And they say that means that it is learning to think more and more. And if you separate them into correct versus incorrect responses, and the left-hand side one basically shows all the increase is really happening in the incorrect responses. Their trace lengths keep increasing quite drastically. And there's barely any change in terms of the correct responses. And a variation of this, an insight connected to this, essentially is that essentially you can actually take, I'll talk about an idea in a minute where you can basically say, if you actually make the model, instead of generating 15 trajectories, if you make it generate 1,000 trajectories and, kind of sort them in terms of increasing intermediate token length, then you have effectively sorted them in terms of increase, you also sorted them in terms of decreasing correctness. So you wind up, get if you generate 1,000 trajectories and take the top 15, then you will have much more solution-rich trajectories that will improve the RL performance. And this has been seen by people in a sort of a roundabout way. So to connect this to kind of the LLM modular stuff I was saying, essentially, I would actually argue that RLVR is a form of LLM modulo, where basically you're taking binary reward. These critiques actually give both binary reward plus the criticism about why the solution is wrong. But RLVR basically just takes the binary reward, and then until it finds a trajectory that is actually correct, or you can generate 15 trajectories and see which ones are getting binary reward of +1 from the model. And so given that, actually, this connection to LLM modulo will give you a couple of ideas. In fact, 3 ideas I'll talk about for improving the DeepSeek R1's RL. 2 of them are kind of already, actually pretty much all of them are already in the air, but I'm kind of giving you a perspective on how to view them. So one idea that I just mentioned on the left-hand side is let the base model increase the number of traces it generates. Instead of generating 15 and checking if any of them are correct, generate 1,000, sort them in terms of increasing length, take the top 15, and then use those top 15 to do RLVR. The moment you do that, you basically, in effect, because of the idiosyncrasies of the algorithm, you essentially have taken more solution-rich trajectories. And the whole point of RL is if you get positive reward, you are likely to learn. If you get mostly trajectories that basically says it's not going to solution, the learning process would be very, very slow. So in general, basically, this is a much a better way to do this. Lots and lots of people have discovered this. One of which is this idea called GFPO, which basically does this. The other idea is rather than just generate 1,000 trajectories, just use LLM modulo to continue generating traces until you get one that is actually correct, that actually incrementally, iteratively generate traces. Instead of generating them parallelly, iteratively generate traces until you find one that is correct. And then the one that is correct, you can then use that in the training. And this is very closely related to doing LLM modulo in post-training. You can call it internal LLM modulo. And I've heard rumors that like Gemini models might actually be doing variations of this. I can't be sure, but nobody wrote a paper on this. But this certainly makes sense if you want to actually get better quality signal to RL. A third way, once you see the connection to LLM modulo, is the critiques are not just giving yes, no, they're also giving yes. And if they say no, here is all the problems with your solution. And that, remember, in the LLM module, I was giving it as a back prompt to the LLM, such that that becomes part of the prompt, and the the conditional generation will change because the prompt now has something about the errors that the critic is saying. This is actually, so I'm sorry. So what you could do is use this richer feedback that LLM modulo gives, as to why the solution is correct, and then include that into the RL framework. And that sort of got discovered recently. And I think, again, it's a very interesting point that people have shown this. I'm just making a connection about these ideas. I'm not saying we did this work. There is an entire area now suddenly that risen in the last 2 weeks called self-distillation methods for improving RL effectiveness. And all that the self-distillation method does, essentially they talk about having, for example, one of the papers from this Andreas Krause's group, for example, talks about having 2 copies of the model. One copy, both copies get the binary feedback, but one of the copies also gets the feedback about what's wrong with the solution if the solution is wrong. And then that, of course, changes the logics of what are the tokens that the second model is going to produce. And then they make the first model, which is getting just the verifier, also follow the distribution that the second model will have on the tokens that it produces. And if you look at it that way, so they call this second model, they call it teacher, but actually they're both students. One student is getting just yes, no reward, and the other student is getting yes. And when they say no, here is where you are wrong. And the first model is kind of trying to learn using the logic probabilities of the second model. In fact, I think you can understand this entire work in terms of just thinking about a single model with richer feedback. So that's a useful thing to keep in mind. That's another way you can improve effectiveness of the RL here. So essentially, if you think of it in terms of like a simple dynamical system, you have the LLM, it is generating tokens, and then this environment right now, basically the old days in the DeepSeek R1 was just the verifier that will give +1, -1 reward. And then now you also have a feedback generator, but to some extent, most verifiers tend to give some kind of a feedback as to why the problem is wrong. And if in fact they simulated it, they'll know where the problem failed, and that actually can be added as the feedback to the model in terms of actually doing the RL on top. So that's a useful thing to understand about how to improve DeepSeek R1 models. So there's a paper basically that talks about all of this except this connection to self-distillation that just happened 2 weeks back. That was also presented at the New Rips that might be of interest to some of you. Now, this is a small digression about what RL in DeepSeek R1 was doing, but the reason I was actually talking about DeepSeek R1's RL is to see if, in fact, even if SFT, we realize that doing SFT, there doesn't seem to be any connection between intermediate traces and their semantics, interpretable semantics from the user's perspective, or even their length and the computational complexity from the from the actual problem's perspective. The question is, maybe RL can actually improve situation. Does that happen? Instead of doing SFT, if you started with a model that's already been SFT'd, and you started doing additional post-training using DeepSeek R1 style RL, and you keep track of how the validity, trace validity, and the solution accuracy keep changing as the number of epochs of RL training increases. Does the validity somehow get more correlated with the solution accuracy? And unfortunately, what we show is that RL always improves the solution accuracy because you are actually training the system based only on the solution accuracy. And it improves it even if, in fact, it's not at all improving the validity. So in the case of even swapped model, where the validity is very low to begin with, it remains low, and yet the accuracy can increase as the number of epochs of the post-training increase. So once again, the intermediate tokens are a scaffold that are helping the learner, but they don't necessarily have any semantics in terms of validity. That is something that our work kind of shows. there's actually a related piece of work that was also presented in NeurIPS, which basically says that what might be happening is that people are confusing local coherence, saying some parts are making sense locally, but you didn't get through the entire trace to make sure whether if you do exactly what the trace said, you would get to the solution the model produced. And this work basically shows that the local coherence tends to increase even when the validity doesn't increase. And that possibly partially explains, that was also a paper in one of the NeurIPS workshops. Now, I want to ask the following question. Well, I kind of talked about these mazes from A-star search and transformers that are empty transformers that are generated, that are basically trained on this. You are about to ask, well, that's not fair maybe, because people basically, if you actually have a pre-trained model, maybe it has more magical characteristics than the ones that are empty transformers. So we have, so basically the question is this an artifact of maze problems, or does it normally have the same problem for other kinds of situations? So we did 2 other papers that I actually want to just tell you the main results of, and you can go back and look at them. Here it's no longer planning, it's like question answering tasks, except it's kind of connected to planning, that these are temporal question answering tasks, saying, has certain thing happened in a certain temporal interval. Okay, and this is called a CoTemp database. And what the students did, what we did basically is just like A-star search can solve maze problems with traces, and it can verify it back. For these CoTemp problems, you can generate traces that basically can be rule-based traces that can be verified. If you produce them, you can verify them too. And then we basically train a pre-trained model, in this particular case, a pre-trained Quen model with a whole bunch of fine-tuned, extra fine-tuning data, which is basically these CoTemp problems, the intermediate traces as produced by these rule-based things which can be verified, and the correct solution. And if you do this, and you again check the connection between the validity of the trace as evaluated in the inference stage and the accuracy, and you also do it with the swapping, the way we did the swapping in A-star search, the results are basically the same. You will wind up realizing again in these papers too, that in this situation too, the verifier, so the trace, essentially, the validity of the trace is not correlated with the accuracy of the problem and accuracy of the final solution. And in fact, training the fine-tuning the model with actually known incorrect intermediate traces by actually doing the swapping of the intermediate traces doesn't actually worsen the performance. Sometimes it even improves the performance. So almost similar to what happened in A-star search, except in a very different scenario where you are actually using pre-trained models. That was presented in that NeurIPS too. And then the last thing that I want to mention here is we actually did this question of, remember, one of the issues that DeepSeek R1 guys did is, if those of you read that paper, DeepSeek R1 folks actually came up with R0 first. And R0 would have intermediate tokens that combine both English linguistic tokens and Chinese linguistic tokens in some arbitrary mix. And they felt that is not understandable to people. And so they then spent a bunch of time retraining the base model to only generate English-looking intermediate traces. That includes huge amount of supervised fine-tuning. And then they did the R1 training with the post-training so that it actually mostly generates English-oriented traces. And the funny thing is actually they found that R1 has lower accuracy than R0. Keep that in mind. Original R0 has higher accuracy than this R1, which only talks English. Because English and Chinese, neither of them have any meaning, so it doesn't really matter what you combine them with to some extent. So we check this only also in terms of their expectation is that if it is in English, maybe it is interpretable to people, at least people who speak English, I guess. So we actually check this in terms of whether is it really interpretable to humans in the loop. And to do that, what we do is we basically train the model with these verifiable traces, which are sharp, and then and I ask the humans whether they actually can make sense of the traces in the inference stage. And we also train the model with R1's traces. So distilled with R1's traces, they go long, multiple pages. And we also ask again the humans if it makes any sense to them. And the weird thing, probably not surprising thing by now to you is that humans find the verifiable traces much more interpretable. They're short and to the point, but the model's performance with those, and the humans also find the R1 traces, the R1-like traces that the model outputs in the inference stage, if it's been distilled with the R1-like traces, to be much harder to make sense of, much higher cognitive load. They don't have any connection to what the solution is. If you actually, do a systematic human subject study with IRB, and however, the meaningless, the R1 traces actually lead to higher performance to the model than the meaningful shorter traces, which sort of tells you once again that what helps LLM and what makes sense to humans are two very different things, and you shouldn't conflate both of them. So that was presented too. Now this sort of kinds of gets you to the almost the last part, which is how does this translate to the frontier models? Unlike our studies, basically in the frontier models, first of all, there are two issues. They basically don't control the data with which the model has been trained, and they don't actually check if it is valid or not in any formal way or any systematic way. And so they just basically take all sorts of data combined, the web level data essentially. And this training data may already contain human-like mumblings associated with the solutions, and the model clearly imitates the style of those. That kind of can explain really the aha moment or let me backtrack now moments, because that sort of stuff is there in the training data to begin with. And since LLMs imitate everything, why won't they imitate the intermediate traces that are present in the training data? One of the other frustrating things is the frontier models do not show their thinking traces, opting instead for sanitized commentaries or summaries. So if you look at the GPT OSS, which is the open source model that OpenAI puts out, they basically make it very clear that they use this thing called harmony format in these models, where there is an analysis part, a commentary part, and a final part. Analysis part corresponds to the thinking tokens or the thinking traces from the R1 perspective. Final is, of course, the final solution that should make sense to the human. And the commentary, they don't actually say how they generate it. None of us know really how that's generated. And most normal users using a frontier model only get to see the commentary, not the analysis at all. So people just somehow look at the commentary and think that's the thinking traces. That's a very different thing from what R1 calls thinking traces. And so that's something to keep in mind. And even in the summaries or the commentaries, they sometimes slip up, as I showed in that Daniel Lit example. There's an overall tendency also in the literature, especially from the frontier labs, to spin the same phenomena that our studies show as only occasional or intentional lapses even. So that picture in the lower left-hand corner shows for the same results, we are looking at them and saying, hey, maybe intermediate tokens help LLMs, but they don't necessarily have to have end-user interpretability. But the same results, similar results can be seen as, hey, LLMs are actually hiding their true intentions. They are actually giving you misleading reasoning traces just so that you don't know what they're thinking about, which is kind of a questionable enterprise. And it becomes harder to evaluate because they are doing it with respect to the models and the traces that they have access to, and we can't even repeat those things. Interestingly, Anthropic originally wrote one of the papers that said, let's think dot by dot, which involved actually putting as intermediate tokens just dots, dot, 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 dot. And if you compare with problem solution fine-tuning versus problem dot, 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 solution fine-tuning, the dot one actually does better in terms of accuracy. So they already kind of were hinting in their own work, was hinting that intermediate traces don't have to have semantics, but generally they somehow hope that at least there are good reasons, I guess, for whatever reason, they're kind of now writing papers saying maybe LLMs are actually misleading by hiding their intentions, and that's worthwhile keeping in mind. One thing that you may want to ask at this point is, why do intermediate tokens improve accuracy at all? because I noticed, basically I'm saying it's not because LLM is thinking like you are thinking like an algorithm, and that would be comfortable explanation, but that doesn't seem to be true. So how can it still be improving effectiveness? Well, part of the way it can do that is the following very simple point, that if you give the task prompt to an LLM, and a prompt, and so look at the right hand side, you give a task prompt to an LLM, and there's a completion from the LLM, and you're asking the probability that the completion is a correct solution. And you compare that probability to giving the same task prompt to the same LLM, plus also giving an extra prompt augmentation. And these are the intermediate tokens. And you are looking, there exists some prompt augmentation. And for some of those, essentially, the completion might well have higher probability of containing the solution than just giving the direct task prompt. That's pretty much what we are saying, that the mumbling is increasing the probability that the conditional probability that the completion will actually correspond to the solution. It doesn't have to mean that those mumblings would make sense to humans in some sort of a cognitively plausible way of thinking about how to solve the problem. If you see this, and if you realize this, especially in the harmony format, if you realize that the harmony format, for example, says that only the solution part is being shown and the commentary part is being shown to the user, and if in fact the intermediate tokens don't have to have any semantics, you can actually mumble to yourself in terms of anything from that dense embedding space. Remember in the very beginning of my talk yesterday, I said ultimately for LLMs, each token is just a vector from the embedding space. Only some finite number of those vectors correspond to actual linguistic tokens. Many others, basically infinite number of others, don't correspond to any single linguistic token. So by definition, you actually, by linear algebra, you can think of them as some arbitrary linear combination of the vectors corresponding to linguistic tokens, modulo some spanning spanning assumptions. And so the thing is, if you allow LLM to then tell itself those latent tokens, and then during the training, then it could potentially tell itself the right kinds of mumblings that actually improve the completion, having the solution, that probability much higher. And to some extent, there is actually work on this showing. There's a Coconut is a system that Meta people have done, and some of the other people have done these kinds of work too, showing that actually doing latent tokens, that means tokens that are actually from the embedding space, but they don't correspond to a unique linguistic token. And so they obviously won't mean anything to the humans, but it still can actually increase the accuracy for the model itself. That's a very interesting thing to keep in mind. So now, why am I making such a big deal about, why not just be happy that maybe sometimes they're in English and they seem to kind of have this comforting English-looking appearance, and maybe people want to think that they are potentially reasoning traces. Why kind of argue against this? Well, there are two issues. One, of course, is they engender false or undeserved trust in the end users. What you're really doing is you're saying, if you don't know how to verify whether the solution I gave you is correct or not, you can look at how I'm thinking and it looks Englishy, so you should feel more comfortable that, okay, this is not a madman. It's saying things like, let me think about the blocks, let me think about the goals. Maybe it knows what it's doing. But that's actually a way of engendering false, undeserved trust in the end users. I give this example to people, and I'll give it to you too. Imagine you have a question for which you truly don't know the answer. You write this question on 2 sheets of paper, and in both sheets, there's the bottom, there's like an actual, a box where you ask the answer to be written, and you give it to 2 different strangers. Okay, and stranger 1 writes in the box, number 7.5. You don't know the answer at all. Okay, so stranger 1 writes 7.5 and writes nothing else anywhere on the page. Stranger 2 writes 3.517 and writes a whole bunch of Englishy stuff in the intermediate space on the page. I would argue that as humans, we have this cognitive flaw that that makes us think that the stranger too must probably know what they're talking about, because they're giving some hand-wavy explanation about why the answer is correct. Even though you don't know which answer is correct at all to begin with, you feel that the very act that somebody tried to give you some kind of an explanation must mean that they know what they're talking about. And that is engendering false trust. Those of you who are students and who took exams where you had a question for which you didn't know the answer and you wrote pages and pages just hoping that the instructor might give you benefit of doubt and give you some partial credit, were basically depending on the same cognitive flaw of the instructor. We don't want AI systems, powerful AI systems, to make attacks on our cognitive flaws. So that's one reason why I don't want to assume reasoning traces have semantics when they actually don't. The second is what I explained earlier, which is, if in fact the traces don't have to be making sense to the humans, they don't even have to be in the linguistic tokens. So you can tell latent tokens in the intermediate traces, and you can have a much higher accuracy. And you might as well do it, because nobody really believes that this mumblings that you're doing is actually supposed to correspond to a coherent explanation. If you want to provide a coherent explanation, that is a separate post facto thing you can potentially be doing. Don't confuse it with what LLM says on the way to the solution. So we actually have a position paper on that saying stop anthropomorphizing intermediate tokens as reasoning and thinking traces. And that too was presented at NeurIPS. And you might be interested in looking at it in terms of the argument that I'm making here. That was the paper that was presented. So in summary, just on the intermediate traces, intermediate tokens produced by reasoning models don't need or seem to have any semantics, even though they copy the style. Solution accuracy can increase even when we train the model with incorrect traces, such as the swap traces. What seems to matter, and we haven't really completely checked this, is the consistency of the traces used in training rather than whether they're correct or not. And what helps the LLMs versus what helps the end user in terms of interpretability are often at odds. That's what we showed in this IRB granted human subject study. And finally, RL doesn't seem to change any of this much. And that's all the stuff that I told you. That gets me to the very last part of this lecture, which is, this is like fresh, like I don't even know whether I'll actually still believe it next week, but this is like a summer school thing. There's stuff that I've talked to you that I've completed, but I also want to tell you stuff that I'm thinking about right now. That's for like the next few minutes. That what if you really want to increase the correct trust that you have in the solution, there are only in two ways. One is you can have external verifiers, or you learn the verifiers and you subject those verifiers to the things that the LLMs provide. That's how you know whether it is correct or not. That's one way. The other is sometimes there may be a situation where you don't know for sure, you don't actually have a verifier for the final solution, but you may have some reasonable ideas about what would be a correct process, what would be the intermediate pieces that the solution that anybody trying to construct the final solution should give. This is like the partial answers to the question. On an exam, imagine you have a question with parts A, B, C, D, E, where like A, B, C, D kind of make you give intermediate answers that go towards the final answer E. And I only look at the answers, not your mumblings or the rough work that you've done on the side. And these answers might very well have problem or domain-specific semantics. And what I would say essentially is you can do meta prompting to tell LLM not only to provide the final solution, but also provide intermediate solutions in specific problem-specific format for which you have verifiers. And if you have that, then the picture looks like this. An LLM has a problem prompt, and the meta prompt says, output the intermediate partial solutions for that problem along with the final solution. And so there would be some thinking, and then followed by some process part, which is basically like a partial solution. Again, some more thinking, some process, some more thinking, some process, final solution. And the final solution is, if you have a verifier for solution, you will verify that using the solution verifier. For the process, again, you can have process verifiers that are again problem specific, and they can check if you're going in the right direction. To give you an example of the kinds of things where this will be useful, for example, a partial solution, for those of you who use deep research, where you ask it to do, find information about some particular topic. typically they tend to give you an abstract plan saying, this is our abstract plan about how I'm going to go about answering your question. Are you okay with this? And if you so, then you say yes, and then you just go and do it. That is actually a solution that it's providing to you because you, the verifier, can make sense of that particular high level plan about how it is constructing the final answer. And you can, if you for example asked it to kind of generate a report about some particular topic, and it said, part of my plan is to kind of go to 4chan and get all the information from 4chan about this topic, you might say, stop doing that. That's not a good plan because I don't trust 4chan, for example. And so that's the way you can, for example, both increase and also push back on the process that's actually being present toward in coming up with a solution. The second, of course, is you might require the thing to provide either sub goals or the partial causal structures, as in the case of planning, and that you can also verify. And there's a paper that will be coming out in archive, like in a day or two, that will actually talk about some of our initial implementations of this sort of idea in conjunction with Microsoft Research. And then, as I said, the process and solution verification can both be based on formal external verifiers or LLM-based verification, which is internal verification, but that will be not sound, but maybe, it's not guaranteed to be sound or complete, unlike formal verifiers. And then, of course, human-assisted verification. In the case of deep research, the abstract plan is basically saying maybe humans can make sense of that rather than the final report. And then if they like the abstract plan, then maybe they'll trust the final report more. This is the kind of thing that we're talking about, increasing the trust in the final solution. So that's basically the idea of increasing the trust in the final solution. And as I said, I already showed you that just self-critiquing doesn't necessarily work. I know I showed you this already yesterday. So in terms of how to improve the correctness, this is all the topics, the sequence of ideas we considered. Standard LLMs don't work. Test time scaling helps, but then it takes time from the user side. Test time scaling can be compiled into post-training. That improves the generator, but doesn't give guarantees yet. You can put a verifier again into the loop. That will be LRM modulo. But if you don't have verifiers, the tempting thing is to assume that the intermediate tokens somehow are giving you information about process, but there is questions as to whether that would be the case. That's what I was showing you. Instead, if you want to evaluate some partial process, you make the question into multi-part question where the partial answers are verifiable by the instructor, okay? And rather than say, write the answer and I'll try to make sense of your mumblings, because that would be much harder in general. And it's definitely harder with LLMs. And also, as I said, the mumblings are supposed to help LLMs improve their accuracy, not to make sense to you. So that leads to the final slide, which I already showed you yesterday, that compared, over the two lectures, I sort of tried to make a bunch of points about, sort of being a little more skeptical about what LLMs are doing with respect to planning problems. They're very, very useful technologies. But in some sense, there has to be some kind of a verifier in the loop. Otherwise, you're talking about trusting the solution just because it looks to be in the correct style. And that doesn't change even with LRMs. It improves, the generator's accuracy has improved, but there's still no guarantees. And the whole thing that I was talking to you about today is, if you're mostly interested in increasing guarantees, what are the various ways in which you can increase the guarantees? And one thing you don't want to do is to depend on the intermediate token semantics, because they don't seem to have any, at least according to our work. And instead, you might do something like process meta prompting, which is something that we just are starting, and there's a paper that's going to be coming out. So I'll stop here. Thank you again for your continued patience. And if there are questions, I will take them right now. It's this time.
Thanks so much, Ron. Are there questions? Well, I would start with one question on the last part you talked about, basically splitting the reasoning, traces into sections, right? And doing process verification. I feel like, isn't it always kind of isn't finding good verifiers fundamentally the hard problem? And like, yes, then finding. finding process verifiers is kind of,
yes. First of all, I understand. Yes, but let's make sure that we understand that all the progress going from LLMs to reasoning models happened only in domains where there were verifiers. So we know that they're hard problem, but it's not like suddenly without verifier, things have suddenly improved. You can have LLM-based verifiers that existed a long time back, but most of the reasoning models performance is in formally verifiable domains such as math, such as programming, and it's a known thing that basically we depend on the verifiers. And I agree with you that if you're anyway depending on the verifier, if you have some information about the process, again, this is not necessarily a way of changing the entire LLM. I'm saying if you took like OpenAI's LLM, but you want to customize it to your particular scenario, then this is what you would do. You would talk about either the verifier for the solutions or partial process verifiers for the solutions that you are looking for, because by itself, OpenAI doesn't care about any specific problem that you might be having. And so if you want to increase the trust in what it's generating, you will have to do that. Okay. Yeah.
Yeah, awesome. Thank you. Any other one?
Thank you for the talk. As a follow-up on your previous comment, as also someone who's comes from a planning background, perhaps this might be a controversial statement, but I think us in the, if we want to see improved performance on LLMs on planning, we need to work on our verifiers in planning, because I would argue that the planning community doesn't really value code artifacts so much. I'm not sure the last time I tried to install Val, but it's not a nice process. So as a planning researcher, should I spend my time more on trying to get LLMs to work with the tools we have, or should I be focusing on writing better tools?
So first of all, I would say it's not a planning specific question. In general, it's understood now pretty much by anybody that the way to improve accuracy of reasoning models in any class of problems is to learn better verifiers for that class first. Either learn or take existing ones. Both of them are possible. In fact, one piece of work that I forgot to show you, that was there in like a ICML workshop long back, is where while LLMs don't work with self-verification, if you take 2 copies of LLM and you train 1 copy to be a better verifier, because you take the same fine-tuned data, for example, and assume every state transition in the fine-tuned training data is the correct transition and every other transition is incorrect, then it will become a discriminative classification task. You can, basically train the LLM to be a better verifier than the standard LLM. And then you make that be a verifier in the loop for the other LLM. That will actually improve performance. So in general, learning verifiers, learning simulators, generating simulators, this is the name of the game. So if you, for example, look at the kind of stuff like people like Andres Karpathy say, this is the same thing. That is, you should be working on better simulators, better verifiers for bigger and bigger classes of problems. What gets lost is people think, hey, it's already doing well in Math Olympiad. I'm pretty sure it will do well in every problem later on. But it's doing well in Math Olympiad because math is one of those things where essentially you have lean theorem provers, you have verification tools on the ready, essentially. Okay, and basically they have done well in programming and math. The coding is like a classic case in point, because coding, you can do self-play if you can actually do generate tests. That's basically the issue. And in coding, it's there because you have the Python interpreter, you have the the unit test. You can guess a code and see if it is right or wrong. And in general, if you want to extend the performance of these models to more and more tasks other than the ones that we are currently looking at, you basically look for verifiers and simulators for those areas. That's just basically the idea.
Thank you. Other questions? I have a question.
Hi, Ron. Thank you very much. I think it's a very great talk. So for just this page, so I think for this kind of task, seems like we have inputs and thinking traits and a solution. So it seems like it is I consider it is a manageable task. So maybe from the input to the solution is a very straightforward task. And but when we need to consider thinking trace, it make the task more difficult. And the evidence of that wrapping the U-shaped experiment, I think, is very great. So maybe it suggests that when we consider the thinking trace, it's not consistent. So maybe there are gradients turbulent when training the model. So is it possible that we so currently I think the loss or the objective is just use the solution correctness to train the model. Is it possible we also consider this process correctness or the thinking trace correctness adding to the loss to make it get the better training results?
So there are, so first of all, two things. You know, please, if you don't mind, I will answer the question as I heard it, but you know, there's a lot more that you said than I was able to actually decipher because of the channel. So please also respond to what I said either on the Slack or you know immediately. But what I seem to understand, one main thing you seem to be saying is, what if you make the training itself be post-training itself be process sensitive? And so first of all, I would mention to you that there existed before DeepSeek R1, there was significant work on process reward models. Okay, the process reward models not basically try to give reward also to the intermediate tokens only if they correspond to a certain kind of a process that leads to the solution. And what DeepSeek R1 guys said is, we tried these process reward models that didn't seem to work so well. So we just stuck to outcome reward model. And in general, it's not a, you know, it's a reasonable point to say that if you have outcome reward and you don't have process reward, sample complexity will be higher, but it'll be easier to kind of train the with less of a signal, but you'll take a lot more training. That's pretty much what DeepSeek R1 went for. And in fact, after R1, lots of people gave up on process reward models. I've heard two things, basically. One basically is, first of all, what I'm showing you here, if you remember that the LLM modulo just had the green solution verification part, and I said I can do that also in the post-training as where you get synthetic data with the solution verification being done by the verifier, and then you use that to kind of, you know, tune the generator with either RL or SFT, right? That is basically post-training. Now that I have this process verifier plus solution verification, essentially the process verifier is the process reward model for me. And so I can do this whole thing also in the post-training. And I would actually argue that the self-distillation, variations of self-distillation can actually be, you know, kind of looking also at the process. And then that basically kind of goes more towards your way. But right now, basically the supervision is only on the outcome in the DeepSeek R1 model. And you are just expecting that somehow magically the intermediate tokens will wind up having interesting semantics, even though the supervision is completely only on the outcome. So if you want the process to have semantics, you have to induce it, either basically by coming up with process reward models. And I would argue that actually process verifier is a way of coming up with process reward models. Process reward models typically tend to be even more specific. So one of the interesting things is, think about sorting problems, let's say, okay? There is, if I give you a sequence, then, and the LLM says, this is the sorted version of that sequence. Any way of checking whether the sorted sequence is sorted is fine, you know. But if you are saying that the LLM is trying to do the algorithm corresponding to bubble sort versus selection sort versus quick sort, the intermediate steps would correspond to very different traces. Okay, because even though the solution is the same, the path to the solution, formally correct paths to the solution, would be different depending on the algorithm. And those all come from process verifiers. So in fact, there is actually, this whole thing is also connected to this whole notion of algorithm verifiability. I'm told that this guy Velacek is coming after tomorrow and day after, and he's people like him have been talking about algorithm learnability in general. That is, how hard is it to learn an algorithm from traces, and LLMs are trying to do it with basically that kind of a work typically tends to consider all kinds of neural network architectures, including graph neural networks. We have actually a paper on graph neural networks and whether they can learn algorithms. But in general, much of this work about are the intermediate tokens have any semantics or not is connected to the question of, did they learn the algorithm or did they learn to approximate the solution? Okay. And the algorithms would be actually multiple algorithms might lead to the same correct solution. And so in fact, making sure that you are following the algorithm is even harder in terms of process. In the verifiers, there could be one verification for the class, a class of problems, but the process depends on which process you are more interested in getting the LLM to do. If you want it to do bubble sort, then you would have a bubble sort process verifier. If you want it to do selection sort, you'll have a selection sort process verifier. So this is built in. This is part of the reason why people walked away to some extent, I think, from process reward models. In terms, at least DeepSeek R1 did. And again, oftentimes these models exist for certain, formal algorithms, just like you have, for sorting, you have not only you have a notion of what is a correct sorted sequence, but you also have, if it is to be called bubble sort, what would be the intermediate steps that lead to the final solution. But for the other problems, there may not be this kind of trace verifiers, and so then you will have to learn the process reward models separately from the solution verifiers. At least that's what I got out of your question. If you're saying something else, please do either ask or write on the Slack so that I can respond.
Yeah, I think you answered my question. That makes sense. Thank you very much.
Thank you.
Thank you. Any other questions? Maybe last question before we break.
Help myself. Thanks for the great two talks. Do you think we're losing something by representing all of these problems as text tokens? You made the point that the intermediate embedding representations are not necessarily interpretable as language tokens. They could be anything. But you also gave an example of, which I found fascinating, of training an LLM from scratch on a token space of 900 something for the maze finding problems. Do you think there's an opportunity in having LLMs self-distill into a token space or domain? Should we have LLMs with math tokens? We have LLMs with geospatial tokens. Does that give us a boost, or are we fine representing everything as text and images?
So once again, let me say the same thing that I said to the other person. This question looks very interesting to me, but again, I could only decode part of it, because of the noisy channel that I'm hearing from. I'm, training myself to hear it correctly, but I think I got the gist of it. I will answer it, and then once again, if I got it wrong, either tell me or write in the Slack. Okay. So the question seems to be, there are like two different questions. One is, are LLMs, because they are in terms of kind of quote unquote linguistics tokens, are they going to lose some generality for problems where the internal representations may or may not correspond to linguistic representations? This is the kind of thing that Jan LeCun, for example, keeps hammering. Okay. Except I would say that to some extent, actually, LLMs are also being used, in things like manipulation, robot manipulation tasks, where the primitives are essentially some sort of like the angles of joints, etc., and they're essentially being trained on that. And so that part probably is not, first of all, two things. I mean, there are enough things that we do with language that if LLMs do those correctly with guarantees, I would still be very happy. I'm one of these people who doesn't understand the whole point of AGI and as to how to define it and why should I care about it. I want to take a tool and talk about, does it have some sort of a guarantees about when I use this, I'm not going to be in big trouble. Okay, so from that perspective, if it actually does well only on the problems that actually have solutions in the language, and that's fine with me. Okay. The second issue is, even if the solution is in the language, the intermediate thoughts, certainly for humans, the intermediate thoughts may or may not be in language. In fact, that's why they say, psychology is a lousy, introspection is a lousy form of psychology. Basically, people get ideas in random places, in random times. My joke is that no mathematician worth their salt will ever say that I came up with this great idea about how to do this proof when I was sitting on the table and I was writing, proof as sketch after proof sketch, and I realized what's the right one. Oftentimes they seem to be getting it when they're going for a walk, or they're in the toilet or something else. And then, of course, they basically will convert that into like a verifiable linguistic process, mathematically, correct proof, and then you get to check it. So to me, the ideas, to the extent intermediate tokens are supposed to be quote unquote ideas for LLM, even for humans, ideas don't necessarily make sense to anybody other than the person who got hit with that idea. And then they will then try to generate some kind of a post facto explanation as to how they thought about this. But that's not exactly how they thought about it at all. It just happened and so that part makes me think that, in fact, that is actually consistent with the fact that if you allow LLMs to tell themselves any arbitrary token from the embedding space, which doesn't even correspond to a single linguistic token. It could be basically, in effect, like a superposition of tokens, with different weights. That actually can increase its accuracy of the, as judged, final accuracy as judged. At which point, definitely, the intermediate traces don't at all look like thoughts; they look like gobbledygook, and that's still. But all you care about is the accuracy has improved for it, separately, right? So that's sort of the way I would look at this. It's not completely clear to me. In fact, one of the things, as you all know, I'm pretty sure you guys are having some lectures on diffusion models, and they're like two big ideas that are sort of competing right now. And it's like a very strange disconnect between the diffusion models, which tends to be like the king of the, king or queen of the area for multimodal data, and especially non-linguistic data. And LLMs seem to be much better for the linguistic data. So the question, of course, is, will there be a way in which actually of understanding what is good for what, and maybe having one single architecture which winds up sort of can be trained with the same sort of data? That's a much more interesting, harder question. I don't have any new answer than the ones that are probably floating about. But I do think that if, in fact, LLMs are actually giving good answers with guarantees for things that we all agree are language problems, then I would be very happy. And most of my talk is about things where, in fact, these are language problems, and you can verify them in terms of language, whether it's a mathematical language, or the planning language, or the English, or whatever. But they actually fall short in terms of the guarantees, and that's what I've been looking at. Thank you.
Thank you, Rao. Yeah, thanks again for the great talk. Hope to have you here next time in person. And yeah, thanks again.
Honestly, you should at least send me some posters or something, don't you think? I mean, I spent like 3 hours talking to you guys, and I have nothing to show for it. It's like early in the morning for you. For me, it's already 5 o'clock. So I can have something, but you didn't send me any. Okay, but thank you. Thank you for your invitation. And thank you, folks, for your attention. I wish I was there so that I could talk to you afterwards, but this is the best we could do. This is recorded. So if you have any questions, please ask me. Thank you again for your attention.
Perfect. Thank you so much.
Bye.